All of you listen question. Explain about intrinsic semiconductor. Mostly like this question they will not ask. They'll ask draw the energy level diagram like that type of things. So what I am telling, whatever points I'll discuss here inside intrinsic semiconductor, that can be questions. Yes or no? So first to write what is intrinsic semiconductor. So everyone write heading 1. Intrinsic semiconductor. Intrinsic semiconductor right, intrinsic semiconductor. What is intrinsic semiconductor? Now the pure form of semiconductor is called intrinsic semiconductor. There are two types of semiconductor you can get, intrinsic and extrinsic. The impure form is intrinsic, the pure form is extrinsic. So pure form of semiconductor is called intrinsic semiconductor. Intrinsic semiconductor. Remember, pure form. And in intrinsic semiconductor, what happens? The number of electrons and holes are equal, basically. So write the number of electrons and holes are equal. The number of electrons and holes are equal. Listen carefully. The next, if I will do a specimen for intrinsic semiconductor, so if I will keep 4 electrons here, I have to keep 4 holes. Holes is basically what? Absence of electron is called hole. Okay. So a virtual positive charge. So if a pure silicon I am taking or pure semiconductor I am taking, then in pure semiconductor what we are observing here? Now concentration of electrons is equal to concentration of holes. That means number of electrons per unit volume is equal to number of holes per unit volume. So give it is n equal to p or Ne equal to NH. So n and p are basically what? Number density of electron and hole respectively. N is the number density for electron, p is the number density for holes. Or you can write Ne, NH. You can write Ne and NH. So for pure semiconductor, your concentration of electron and hole are equal, or number density of electrons and holes are equal. Yes or no? So this one remember. So write down. This is a basic idea about intrinsic semiconductor. The most important question will be here, energy band diagram. You draw energy band diagram for intrinsic semiconductor at T 0 Kelvin and T greater than 0 Kelvin. You draw that. So that will be question. So that one will try to do now. Energy band diagram will try to do. Please all of you write. Holes means absence of electron. Absence of electron is called basically what? Hole. Okay, you take one piece of paper. From that paper you make a hole. How you make a hole in a paper? If you will remove some portion of a paper from that, it will become hole. That means when paper is absent, then hole will come. Yes or no? Yes. So similar way, when absence of electron is there, that time what will happen? Hole will. So hole is basically considered as a positive virtual charge. Okay. Suppose you have bond here. Suppose in silicon material, suppose I am checking here silicon. So like these silicon atoms are bound to each other. Silicon atoms are bound to each other. Now two silicon you take. Two silicon take and explain. Now see here. Now here two electrons are there. One silicon is bound to another silicon. Okay. Now suppose due to thermal energy, if this electron, whatever two electrons are present here, their bond is there, that bond is breaking. If this bond is breaking, what will happen? Now these electrons will come out. If electrons comes out, what will be present there? What will be present there? Now here you will have absence of electron. Here what will have? Absence of electron. This absence of electron is called basically what? Holes. Yes or no? So hole electron number is same in semiconductor. And remember, for semiconductor, charge carriers are both electrons and holes. Okay. But if extrinsic semiconductor will take, that time again two types, p type, n type will come. We'll discuss separately in extrinsic semiconductor. NH or NP, anything you can take. Okay, here we are asking, right? Here you can write N subscript H or N subscript P, no worries. But mostly NH taken, NH, Ne. So remember this intrinsic semiconductor. Now next to come energy band diagram, which is most important. All of you listen carefully. So write energy band diagram, energy band diagram of intrinsic semiconductor. Intrinsic semiconductor energy band diagram you check. See here, first you do one conduction band, another do one valence band. Okay, here you take electron energy, and here I'll keep some energy levels like this. In conduction band also I'll keep some energy levels. And this diagram, whatever I am doing, that is energy band diagram. Listen carefully all of you. This is for T. At T equal to 0 Kelvin I am doing the diagram. T equal to 0 Kelvin. And here I have taken electron energy. And this topmost valence band I'll give as EB, and lowest most conduction band I'll give as EC, and you know I'll write this one as valence conduction band, and this one is your valence band, and here I'll keep some electrons. So for T equal to 0 Kelvin, here T equal to 0 Kelvin, what happens? All the electrons I'll keep here, all the electrons. Okay, here all the energy levels are occupied by the electrons at a T equal to 0 Kelvin, and conduction band is empty. No electrons are present there, so conduction band is empty. So for T 0 Kelvin, intrinsic semiconductor will behave like insulator. It will behave. Yes or no? See this dot whatever given now, these are basically electrons. And all of you listen. In one energy level, you can have 2 electrons. That's why 2 dots I have given. Okay. So 2 dots are given. So this is T equal to 0 Kelvin. Similarly, do the diagram for T greater than 0 Kelvin. T greater than 0 Kelvin do first conduction band here. This is your EC. And down you do valence energy band. Okay. All energy levels keep inside. Similarly, you take electron energy here, electron energy taken. This one you write EV. This is your conduction band. This is your valency band VB. Conduction band is CB. Now here what will happen? For T greater than 0 Kelvin you take. This is at T greater than 0 Kelvin. That means some temperature is given. So when temperature is given, what will happen? Now electrons will get thermal energy and they will try to go to conduction band. They will move to conduction band. Yes or no? So that energy bands which is near EV, that band's electrons will move to conduction band. So here I'll keep as a hole, like this one hole I'll keep. Empty circle. Empty circle represents basically hole. So that 2 electron has gone to conduction band. So I'll write here. Dot dot I'll write here. Okay. So this is your this is your what? Energy band diagram for T 0 Kelvin left side, for T greater than 0 Kelvin right side. And this one you can consider as your energy gap. Whatever this one is here, this is your EG. EG means energy gap. This is your basically what? EG. Energy gap is there. Okay. So like this graph they can ask you. This is important. 3 marks they'll ask you to draw the diagram for 0 Kelvin, and when T equal to 0 Kelvin, that time no electrons in conduction band. You see, conduction band is empty. Yes or no? Conduction band is empty. Only electrons are there in valence band. 2 electrons you keep in each energy level, and all this energy level of valence electron is called valence band VV. Yes or no? Now next. For T greater than 0 Kelvin, these electrons, see whatever electrons are here, these electrons got some energy. These electrons, whatever electrons are there in valence band, they got some energy. Then they went to up. They went to conduction, higher energy level they went. They went to conduction band. Yes or no? So that's why there is empty. Empty circle basically represents holes. You write here, this is dot, whatever dot in yellow color I have done here. Let's give that. This represents basically electrons. Electrons. And this one represents what basically? Hole. This is a hole, that is a electron. Electron and hole. Okay, solid dot circular dot is electron, hollow circular is what basically? Hole. Empty circle. Empty circle is clear idea. So filled circle is basically electron, empty circle is hole. Yes or no? So this diagram you should remember. 3 mark question or 2 mark question they can ask to draw the diagram. Now next we will do covalent bond diagram for silicon at low temperature, and we will try to understand what is happening there. Okay. So everyone understand carefully. Remember the points. Okay, now here they will ask you explain about intrinsic semiconductor. If they ask you, you can write all together everything. But mostly some certain things, some 1 mark question they can ask. What is the concentration of electron hole relation? Okay, and what is the energy band diagram? That type of thing questions they can ask. Shall I go to next point? Draw everyone. All of you, this one you keep empty circle. One is filled circle, one is empty circle. You check here carefully. Whatever I have done here, these are basically empty circle. Yes or no? Empty circle. Empty circle na, like this you do. Like this. Empty circle, one is solid circle. Yes or no? So be careful. While doing the diagram, be careful. Empty circle, solid circle. Now next listen. See, can you say why this empty circle came here? Because electrons are previously to are there when temperature is greater than 0 Kelvin. So these electrons got some energy, thermal energy. So they got excited to higher excited state. Yes or no? Or they went to conduction band. Clear? Okay. Next listen. Next page. Right? Covalent. Covalent. Next point, right? Bond. Covalent bond diagram. Covalent bond diagram of silicon at low temperature. According to covalent bond, you will see how the silicon crystal will look like. How the crystal of silicon will look like. So I am drawing this one. You draw, please. So here you keep silicons. Okay. So 3 silicons in one row. Again 3 silicons in another below row. Again 3 silicons in another below. Now what you do here? Now one electron you take and make bond here. So each silicon will have 4 valence electrons. Each silicon having 4 valence electrons. Okay, yes or no? Now what will happen? This electron they will share and they will make bond. Yes or no? Do like this. See, each silicon having 4 valence electron. That one I am writing. Okay. For each silicon you give. Now next listen. Now electron you consider. These 2 are forming one bond. These 2 are forming one bond. These 2 forming one bond. These 2 are forming one bond. These 2 also forming one bond. This also forming one bond. This also forming one bond. This also forming one bond. Like this one you can take. This also forms one bond. This also bond. Here also bond. Here also bond. 2 electron will form one bond, right? These are covalent bonds basically. Draw, please. Yes or no? So this is the covalent bond diagram of silicon. Instead of giving like this, you can do also like this one. If it 2 silicon you have taken, in 2 silicon one bond you can make, 1 electron here, one other electron here. You can substitute like this. You can put like this also. You can do the diagram like this. Okay, or you do like this. Whatever I have done here now. So this is the covalent bond diagram of silicon crystal. Okay. Si is basically silicon atom. Si is what basically here? One Si is silicon atom, and dot is nothing but dot is one electron. Okay. Hey, please sit down. Darshan. Note it down, all of you. Now some other points will write current conduction. How current conduction takes place in intrinsic semiconductor. Completed? Completed or not? Next, right. The current conduction takes place by both electrons and holes in pure form of semiconductor. So that point you write, everyone. So write the conduction current conduction takes place due to both electron and holes in pure semiconductor So write current I, total current equal to current due to electron plus current due to hole. Current due to electron plus current due to hole. Write down, ma. Hello. So someone asked you what is current, total current in a pure form of semiconductor. It is because of electron also, hole also. So this is due to I, due to electron also, due to hole also. So total I equal to IE plus IH. I is the current due to electron. IH is what? Current due to holes. Now similarly conductivity expression also you can write. Conductivity expressions. But intrinsic semiconductor, yes, all the points. But specifically I am telling energy band diagram is important. I don't know T equal to 0 Kelvin, T greater than 0 Kelvin. That diagram in exam they will ask 3 mark question. Okay, so you prepare that energy band diagram. This one, this. So be careful about that. Shall I go next page? You please complete this. Complete. 2 minutes wait. This things will get over. Yes. Alright, conductivity in intrinsic semiconductor. Complete fast. Completed? Listen here. Conductivity in conductivity expression in intrinsic semiconductor. So what is the conductivity expression will come here? All of you listen. Conductivity will come due to electron also, due to hole also. The conductivity due to electron is nothing but N into mobility of electron, concentration of electron, mobility of electron into E plus concentration of hole, mobility of hole into E. E is basically electronic charge. So like this conductivity will come. Now here you can take E common. Then you can write it is Ne mu E plus NH mu H. Now here if Ne NH they are equal here actually. So I can take common. I can make it Ni. I take common Ni into E equal to mu E plus mu H. So I'll write here what I considered. Now Ne and NH, they both are basically equal in intrinsic semiconductor. That is I am considering is Ni. And what is Ni I am telling here? Now Ni is nothing but it is called concentration of or intrinsic concentration. Right here it's called intrinsic concentration. It's called intrinsic concentration. Okay. So now this one sigma expression you remember. Sigma is conductivity in intrinsic semiconductor. Where mu E, mu H, basically mobility of electron and mobility of hole. So right here where mu E, you can write mobility of holes, and mu H, remember it is mobility of electrons. Mu E is mobility of electrons. Mobility of electrons, and mu H right mobility of holes. And remember mu E will be greater than mu H. And Ni, remember this Ni how represented with the temperature and all. Now A T to the power 3 by 2, a constant into T to the power 3 by 2 exponential minus Eg by 2 kBT minus Eg by 2 kBT. Minus Eg by 2 kBT. Kb is Boltzmann constant. Okay. So remember Ni is directly proportional to T to the power 3 by 2. This also you remember here. Mobility of electron greater than mobility of hole, and intrinsic concentration is temperature power 3 by 2. In exam questions are coming. Intrinsic concentration how related to temperature. Okay. Remember it is what? T to the power 3 by 2. Okay, write down. A T to the power 3 by 2 Ni. Intrinsic concentration. A T to the power 3 by 2 exponential minus Eg by 2 kBT. Remember this formula. So you understood about conductivity expression, no doubt. Okay. Now last point, listen. At 0 Kelvin, how intrinsic semiconductor behaves and what is its resistance? At absolute 0 temperature or T equal to 0 Kelvin, intrinsic semiconductor basically behaves like insulator, and resistance will become infinity. That one we'll see next. All of you complete this. Next one is variation of semiconductor, or what is the effect of mu H, mu E plus mu H. Mu H is mobility of holes. Mu H, right? Which one? This one. Mobility of electrons. Ni equal to A T to the power 3 by 2 exponential minus Eg by 2 kBT. 2 kBT, K subscript B, that is Boltzmann constant. Capital KB is basically Boltzmann constant. 2 kBT like this written, okay? Ni value. But remember, Ni directly proportional to T to the power 3 by 2. This thing you would remember. Over intrinsic semiconductor. Yes or no? Now next one more point, listen. All these points together, remember, anything can be questions or MCQ or anything, 2 mark, 3 mark. But in this energy band diagram, draw is important. Draw the energy band diagram for intrinsic semiconductor for T 0 Kelvin and T greater than 0 Kelvin. Next page, listen. Semiconductor, right? At absolute zero temperature. At absolute zero temperature, that means T equal to 0 Kelvin. Semiconductor or intrinsic semiconductor also you can write. Semiconductor behaves like an insulator. Please go to your place. At absolute zero temperature, semiconductor behaves like what? An insulator. Yes or no? Next, you can write what is the resistance. Now at T equal to 0 Kelvin, resistance of semiconductor is equal to R, which is infinity. Listen, what is the resistance? Resistance of semiconductor is infinity. Or you write like this also, no worries. Resistance of semiconductor is infinity. Why infinity I am writing? Because it is becoming insulator at 0 Kelvin. So that means in bracket you write R equal to infinity. Okay. So this much idea you remember about intrinsic semiconductor. Clear? All of you got the point? Yes. And this energy level diagram will be most important part. Okay, you remember that. Okay. T equal to 0 Kelvin, T greater than 0 Kelvin, how energy band diagram is represented, you understand that. Okay, in this intrinsic semiconductor. So that's all about intrinsic semiconductor. Please write down. So it includes here, this is the first page, this is your second page, this is the third page, this is the fourth one, and this is the fifth one. Yes or no? Clear? No doubt? Okay. Note it down. Thank you.